Hello everyone, I hope you're all doing well. So in today's video, we are pretty much going to go through the 2023 physics exam short answer questions part 2, where we'll be pretty much continuing off from questions 10 to 17. And so like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah guys, let's smash through this video. Question 10. A proton in an accelerator beamline of proper length of this has a Lorentz factor of this. Alright. Calculate the speed of the proton relative to the beamline in terms of c, the speed of light in a vacuum. Give your answer to 3 significant figures. You don't even need to be scared when it says relative to the beamline, because you remember the speed of light is constant through basically any observer, basically. It's always constant. So we just need to calculate the speed of the proton. Now, let's do that. So what we basically need to do is, because we have the Lorentz factor, there is a formula that is basically transposed. You should have this formula in your formula sheet. We know that velocity is c square root 1 minus your Lorentz factor squared. So basically going backwards to get your velocity. So this is a very important key formula. Make sure you put it in your formula sheet. It's very important. And so now let's do this. Basically all we have to do is c square root 1 minus basically 2 squared, which is going to give me minus 1 4. That gives me basically velocity basically is 0.23 significant figures. That's 0.866 c. Beautiful. So write that down. Right. 66c. Beautiful. Calculate the length of the beamline in the reference frame of a proton. So we know in the proton's frame of reference, it's going to be length contraction. So the length is going to be contracted. So we just want to calculate the length contraction. So we know the length contraction is your proper length over your gamma, or your Lorentz factor. So our proper length is basically 4.8 divided by your gamma, which is 2. That gives me 4.82 basically gives me 2.4 kilometers. All right. Calculate the kinetic energy of the protons in joules. Show you're working out mass of the proton. Now look at this question. I think this is a key here. So basically when you get questions like kinetic energy, now in terms of classical physics, you know you would use half mv squared. But you got to remember this here. We have relativistic speeds at this point. So we're basically going to use our kinetic energy for relativistic speeds. And yeah, normally when you get questions and you sometimes get confused, you're like, what is it? What, like, they would normally give you a statement like, ignore relativistic speeds or relativistic effects. But here, they haven't said that. So this question, it's about talking about relativistic kinetic energy. And yeah, because remember, you're going at this basically close to the speed of light. So yeah, so we know that kinetic energy in the relativistic effects is your gamma minus 1 mc squared. So basically, it's going to be 2 minus 1. Yep, it was 2. Yep, 2 minus 1. The mass of the proton, which is 1.67, times 10 to the negative 27, times your c squared, which is 3.0, times 10 to the power of 8 squared. So that's going to give me 1.67 times 10 to the negative 27, 3.0 times 10 to the power of 8, all being squared. That gives me basically 1.50 times 10 to the power of negative 10 joules. Beautiful. Next question. Question 11. A guitar of the length of 0.75 meters and fixed at both ends is plucked and a standing wave is produced. The envelope of the standing wave is shown in figure 13. The speed of the wavelength along the string is 393 meters per second. What is the frequency? Okay, so we know it's basically fixed at both ends. Let's look at the frequency formula for fixed at both ends. All right, so frequency, right here. Frequency is NV over basically 2L. Now, so we're basically, this is your fundamental harmonic. So N equals 1. Straight away we can see that. So it's going to be basically your velocity, which is 393 actually, divided by 2 times your length, which is 0.75. That gives me 393 2 times 0.75. Basically, 262 hertz. Yeah. Describe how a standing wave is produced on a string fixed at both ends. I've seen this question quite a lot of times in exams, and basically this is what you just need to say. So we know that standing waves overall are basically formed when two waves of certain frequencies, there have to be certain frequencies, not all, remember from this formula, not all frequencies create a standing wave, only certain of them. Basically, yeah, so certain of them will create a standing wave, basically, so only certain frequencies, and what happens is those two waves basically superimpose with their reflection ones. So they'll reflect along those two ends, and so those its reflection will basically superimpose with it in the opposite directions. So one will go, let's say one goes basically like this to the right, while other one goes backwards. And so basically when they basically come together, they're going to superimpose. And so basically, but make sure one's reflected. What am I doing? One was actually reflected, yeah. One has to be reflected. So basically when they're coming together, they superimpose, and hence we get a standing wave. And make sure they are in the opposite direction. One's traveling, they're both traveling at the opposite directions, yeah. I mean, it's only 2 marks, so I think the first mark basically comes from saying that it's basically two waves, basically traveling like at certain frequencies, and basically they superimpose with their reflections in the opposite direction. Those are the 2 marks I think you get. So it's not too bad for 2 marks. Wow. All right, let's write those down. Okay, let's go. So we can say standing waves are formed when traveling waves, so you get traveling waves, so when traveling waves of certain frequencies certain frequencies are superimposed with the reflections traveling in the opposite directions. In the opposite direction. Beautiful. That's it. Next question, question 12. Let's have a look at this. A ray of monochromatic light is incident on a triangular glass prism with a refractive index of 1.52. The ray is perpendicular to the side AB, of the glass prism as shown in figure 14. The ray of light travels through the glass prism before reaching the side AC. So basically it goes through it like that. It basically passes through it. And so before reaching, side AC, we can see, calculate the critical angle for the glass prism at the glass air interface. So, all right, so we're going to have a look at here. This is like a straight line, so we have to draw a normal to kind of visualize it. So I'm going to draw the normal like this. It has to be basically perpendicular, like that. So you can see that's perpendicular. All right, now what do we know? Well, we know the critical angle is basically the angle from this normal, from the yellow line. It's like an angle from the normal. Why is it? Basically an angle from the normal. Ooh. Okay, I'm just going to draw like this then. It's like an angle from the normal where you get basically a critical angle that it's between the basically the glass and the air interface. Yeah, that's our critical angle. So it's just the angle here. Calculate our critical angle. So let's do that. All right, so critical angle formula is basically N1 sine theta C equals N2. We're going from the refractive index of the glass prism, 1.52, sine theta C is what we're trying to calculate, and N2, we're going basically to the air. Hence your theta C is basically your sine inverse of 1 over 1.52. So you get 1.52. And so basically that gives you around 41 degrees. All right, so that's our angle. So that's basically our angle. So 41. All right, so yeah. Okay. Will the ray of light undergo total internal reflection at the side AC of the rectangular prism? Justify your answer. All right, let's have a try to look at this. Okay, so if our refractive index, so if our critical angle is here, and our incident ray, basically, you can see that the incident ray's angle from the normal is greater. You can see it's greater than your critical angle. So remember, if your incident, we know that if your incident angle is greater than your critical angle, total internal reflection will happen. So the light will basically, this is what will happen. So when that beam when that beam goes basically in there, it's going to be basically reflected. Like that. So it's going to be backwards. It's going to come back. And so, yeah. So let's write that down. Basically, we'll go, yeah, let's write it nice. Like a nice statement. So it will undergo total internal reflection as the incident angle, which is 45 degrees, is greater than the critical angle. Critical angle, which is 41 degrees. Beautiful. That's nice. Question 13. Let's have a try at this. This is a color. What color should we use? A nice color. We'll use brown, actually, this color. A group of physics students undertake a young double slit experiment using the apparatus shown in figure 15. They use a green laser that produces a light with a wavelength of this. The light is incident on two narrow slits, S1 and S2. The distance between the two slits is 100 micrometers. All right. An interference pattern is observed on the screen where P0, P1, and P2 being the location of adjacent bright bands. Okay, so bright band means where constructive interference happens, shown in figure 15. Point P is the central bright band. All right. Calculate the path difference from S1, P1, so S1, P2, and S2, P2. So, okay, easy. Give your answer in meters. Show you're working out. Beautiful. So, we know the path difference. So the path difference is, well, we know that at P2, it's constructive interference. So we know path difference is basically n pi for constructive interference. We know it's the second, basically the second bright band. So we can put 2 lambda, and hence, what's our wavelength? 510, so 510 nanometers, -9. That's going to give me 2 times 510 times 10 to the -9. So basically 1.02 times 10 to the power of 1, 2, 3, 4, 5, 6. -6 meters. Beautiful. Is that right? 1, 2, 3, 4, 5, 6. Yep. The green laser is replaced by a red laser. So if you're basically replacing a green laser with a red laser, you've actually decreased the frequency. So hence you have increased your wavelength. If you decrease your frequency, remember if the opposite happens to the wavelength. So yeah, you replaced by a red laser. So the green is replaced by the red laser. All right. Describe the effect of this change on the spacing between the adjacent bright bands. Okay, easy. So we know that the bright bands, the spacing is given by lambda L over D. So if we know that our lambda or our wavelength has increased, it means our spacing also has increased. Because it's 1 mark, we just have to say that. Just say it's increased. So the spacing has increased. Oh, why did I not delete? Okay. So the spacing has increased. Beautiful. Explain how Young double slit experiment provides evidence for the wave-like nature of light and not the particle-like nature. This is one of the most easiest questions. It comes up in every, so how many exams have I done? And it's always a repeating question. This is so easy to get full marks. So the way you get the full mark, it says, explain how Young double slit experiment provides evidence for the wave-like nature of light. And so that's normally 2 marks in an exam, but this one's 3 because it also tells you and not the particle nature. You have to give an extra information why the particle-like nature doesn't explain the Young double slit experiment. So it's very easy in terms of the wave-like nature. So because first, this is all you need to explain. Well, we can see that there is bright bands and dark bands that would be produced basically. And so this actually, the young double slit experiment basically demonstrates interference. And you know, remember, interference is a wave phenomenon, and hence basically the wave model supports it because it's a wave phenomenon. And that's why basically you get those two marks by basically saying those two, because that's why it supports the wave model, the young double slit experiment. But the next mark basically comes from, okay, it says why and not the particle-like nature. Okay, well, let's think about the particle-like nature here. So we know that the particle nature, what it predicts is that you basically get, say you have this laser, what it's going to happen is basically when the laser hits, is basically they should have seen what the particle model basically predicts is those, in those two slits, when the laser hits, there's just only going to be two bright bands here, basically. So when the laser hits, there's, you know, it was like a hypothesis, they hypothesized, they even predicted that, you know, there should be two bright bands only here. But they realized that there was a basically like an interference pattern. So yeah, you just need to basically explain that. Just be like, when like the particle model basically would have predicted that the bright spots would be between there will be two bright spots, basically be like, you know, in that slit that go through the slit, and that doesn't occur. So it only supports that wave phenomenon, the wave model. Beautiful. That is it. So let's write that down. All right. So young double slit experiment demonstrates interference. That's where the first mark comes, basically. The second mark basically saying interference is a wave phenomenon. Thus, the wave model is supported. And so now we just have to talk about like why the particle nature doesn't work. So because basically the particle model predicts a bright spot, basically a bright spot behind each slit. So bright spot behind each slit, which does not occur. Beautiful. I think that's it. We don't want to write too much on that one. Yep. Question 14. Neutrons are subatomic particles, and like electrons, they can exhibit both particle-like and wave-like behavior. Ignore any relativistic effects. A beam of neutrons that can be used for scientific experiments is produced by a nuclear research reactor. The mass of the neutron is that. The de Broglie wavelength of the neutron produced by the nuclear reactor is this. So that's a wavelength. Find the speed. Easy. So, of these neutrons. So we know that we're given the wavelength. All right. We know that the wavelength is h over your momentum. Meaning, and we know momentum is basically mv. So, rearranging it to get velocity, we get mv equals h over wavelength. And timesing both sides by 1 over m, we get v equals h over m wavelength. That is your formula, basically. That's the formula that we're going to use to calculate our velocity. Put there. Let's go. So, we want it in meters per second, of course. So, just put... So, your 6.63 times 10 to the power of negative 34. Your mass is 1.67 times 10 to the power of negative 27 times your wavelength, which is 3.02 times 10 to the power of negative 10. So putting that, I should get 6.63 times 10 to the negative 4. 1.67 times 10 to the negative 27. Basically 3.02 times 10 to the negative 10. Beautiful. So I get, so 1.31 times 10 to the power of 3 to the power of 3. 1, 2, 3. Yep. Beautiful. The neutron beam is sent through a crystal with an intraatomic spacing of this. Would you expect to observe a diffraction pattern? Justify your answer. So we know that for diffraction to occur, we know that the ratio, which is wavelength over width, must be basically greater or equal to 1, or not just greater or equal to 1, just approximately close to 1. Approximately anything close to 1. Normally, yeah, so let's see what it is. So doing this ratio, basically, we know the wavelength, so the width is equal to, well, what's our wavelength? 3.02 times 10 to the power of -10 divided by your width, which is basically the interatomic spacing, which is 3.62 times 10 to the -10. That gives me 3.62 times 10 to the -10. And that gives me basically 0.834. Now, this may seem like it's very small, but it's actually close to 1. It's very close to 1. Normally, when like diffraction doesn't happen or it's insignificant, it's when it's like 0.01, when it's so small normally. And so that's when basically you don't get any diffraction. But here, this is actually close to 1. So there will be some minimal diffraction. So you would expect an actual diffraction pattern to basically happen here. So, all right, let's now write something. So we're going to basically say diffraction depends on this, so your ratio. This is close to 1, hence we would expect to be able to observe diffraction, a diffraction pattern, basically. Diffraction pattern. Beautiful. Consider an electron beam with the same de Broglie wavelength as the neutron beam. So it has the same wavelength. Which will have a greater speed, an electron in the electron beam or a neutron in the electron beam? Okay, so they both have the same wavelength. Okay, so remember how we said that wavelength is what? We said that it was h over momentum, which was mv. Yep. And so we rearranged it to get velocity, which was basically h over m wavelength. Okay. C. H is constant, and also your wavelength is constant because both of them have the wavelength. So the only defining feature is their mass. So the bigger the mass, the lower the velocity because you're increasing your denominator. The lower the mass, the higher the velocity. So which one will have a greater speed, an electron or a neutron? So basically, if we want the higher speed, it's the one with the less mass, the one with the smallest mass. So we know that electron has a mass of basically 9.1 times 10 to the -31, which is quite small. What about the neutron was? It was 1.67, so 1.67 times 10 to the -27. The electron actually is so much smaller. So guess what happens? It means your electron is basically the one that goes at a greater speed. And that is it. Let's just basically, I'm going to rob this out. I'm going to write it now. And more nicer plot. So we know that the electron is, so basically 1 mark comes from electron. Speed is greater. And so electron has less mass. Hence, using V equals what's h over mass wavelength, the velocity is greater. Beautiful. So now, question 15. In a photoelectrical effect experiment, a team of physics students investigated the relationship between the maximum kinetic energy of ejected electrons and the frequency of the light incident on calcium metal. The results are shown in figure 16. All right. Beautiful. Using the data from the graph in figure 16, estimate the work function of the calcium. Beautiful. So remember, the work function is just basically your y-intercept, which is 1, 2, 3. It's basically 3.0 electrovolts. Done. Using the data from the graph in figure 16, determine the maximum wavelength of light that can emit photoelectrons from the calcium surface. Easy. So basically, to determine that, all you need to determine is the threshold frequency. So let's estimate the threshold frequency here. We can see that's at 6, 7, around 7.3. Around 7.3 it looks like. So if your threshold frequency is 7.3 times 10 to the power of, what was it? 14. We know that, of course, that your wavelength is your speed of light over your frequency. Hence, it is just going to be 3.0 times 10 to the power of 8 divided by that 7.3 times 10 to the power of 14. 7.3 times 10 to the power of 14. So that gives me, that looks good. So it gives me basically 4.1 times 10 to the power of, so 1, 2, 3, 4, 5, 6, 7. -7. Is that right? So 1, 2, 3, 4, 5, 6, 7. Yep, -7 meters. Beautiful. The calcium metal was replaced with a copper metal with a work function of 4.7 electrovolts. On the grid in figure 16, draw the graph that would result with the calcium metal was replaced with copper metal. So basically, it's a 4.7 electrovolt. 4.7 electrovolt, which is 4.7 around here. So what it's going to have is basically it has the same gradient as your calcium, basically, but basically translated down to the y-intercept to be that 4.7. There we go. So basically, this is how it would basically look like. That is your, what was it? Copper? Yep, copper metal one. So this one's your copper metal. Beautiful. So the copper metal is illuminated by photons of wavelength of 300 nanometers. Will photoelectrons be ejected? Justify your answer using calculations and any relevant data from the graph. Easy. So what do we know? We know the work function. We just need to determine the energy of those photons, and if energy of the photons are greater than the work function, then photoelectrons are ejected. If they are less, then they're not ejected. Easy. So energy of photons basically is, because we're giving the wavelength, so it's going to be hc over wavelength. So it's going to be 4.14 times 10 to the negative 15 times your speed of light over your wavelength, which is 380 times 10 to the negative 9. 4.14 times 10 to the negative 15. 3.0 times 10 to the power 8. 380 times 10 to the negative 9. And so basically I get 3.27 electrovolts. Now, you can see that this energy is less than the work function, so no photoelectrons will be emitted. So basically, as energy of photons is less than the work function, basically, no photoelectrons, yep, so photoelectrons are ejected. Beautiful. Question 16. Fluorescent lights, when operating, contains gaseous mercury atoms, as shown in figure 17. All right, that looks good. Analysis of the light produced by fluorescent light shows a number of emission spectral lines, including a prominent line representing a wavelength of this. Calculate the energy of the photons represented by the emission spectral line representing this wavelength. Easy. So, basically it's just the energy of photons, which is hc over wavelength. So we want electrovolts, so it's going to be basically 4.14 times 10 to the negative 15 again. So 15, that's constant, times the speed of light. All being divided by your wavelength, 436.6 times 10 to the negative 9. 4.14 times 10 to the negative 15. 3.0 times 10 to the power 8. 4, 3, 6.6 times 10 to the negative 9. Yep, 6 times 10 to the negative. That gives me basically 2.84. 2.84 electrovolts. Let me write that nicer. Beautiful. So figure 18 shows the lowest 5 energy levels for mercury. Okay, on the diagram level, so on the energy level diagram in figure 18, draw an arrow showing the energy level transition that corresponds to the production of the spectral line representing the wavelength 436. The same wavelength as this. So we already calculated the energy that would release. So all we need to do is find which one it is. Let's try 6.7 minus 4.89 first. Does that give you the same? So 6.7 minus 4.89. No, that's too small. So try the next one. So basically, that minus 4.89. 7.73 minus 4.89. 2.84. Yes. So it's basically from here to here. That's where basically it will emit. That spectral line will be there. Okay. A 6.7 electrovolt photon is absorbed by the mercury atom in the ground state, and then the atom transitions back to the ground state. Identify the energies in electrovolts of all the possible photons that could be produced. Okay, so basically what it says is a 6 electrovolt photon is absorbed by the mercury atom, so it was at the ground state. It says 6.7 would basically make it here basically now. That's 6.7. And so it transitions back to the ground state. State that identified the possible. Okay, easy. So we know that, it could possibly basically just go down. It can possibly go down here also. And it can also go from here to here. So these are all the possibilities basically. Beautiful. So basically you just need to write those, which the first one is 6.7 electrovolts. The other one is 4.89. So 4.89. And the little one is basically 6.7 minus 4.89. 4.89, which is 1.81 electrovolt. Done. Question 17. J.J. Thomson discovered electrons in 1897. He used evacuated cathode ray tubes to determine the ratio of the electrical charge to the mass of these rays, which we now know were electrons. Modern day physics students plan an experiment to measure the ratio of the charge E to the mass M of electrons. This can be written as E over M. This apparatus they used is shown schematically in figure 19. An electron gun ejects a beam of electrons horizontally from the left side of the apparatus through the evacuated glass tube. Fluorescent screen displays the path of the electrons taken. All right, beautiful. The electron gun can be modeled as shown in figure 20. Electrons are produced at the electron source and accelerated between A and B. So those plates. Okay, makes sense. Electrons reach plate A with negligible speed and are accelerated by the potential difference between the plates, which is your V0, emerging from plate B with a speed of V. Write an equation that gives the speed V in terms of the potential difference V0, the electron mass, the electron charge, assuming that V is much less than the speed of light. All right, this is not too bad. So just basically use your electron gun formula. So we know the electron gun formula is half mv squared is equal to QV. Now, Q, basically, it's the charge, but they want to write it in E, so we're going to write it as EV. E, basically V naught, because V is, your voltage is in naught, so we just want to calculate the velocity. So times both sides by 2, we get 2EV naught. Divide both sides by M, and then square root it to get basically your velocity. That's your formula. Easy. An electromagnetic field B directed into the page is applied to the regional fluorescent screen, and the electrons follow a circular arc of radius r as shown in figure 21. Okay. Explain what the path followed by electrons is a circular arc. A very, very easy question, comes up in many exams. A lot of exams. Always the same question. It always comes. All you need to state is, it's only 2 basically marks. All you need to say is this. The magnetic force acts perpendicular to both the velocity and the magnetic field, of course. And also, this force is always present and of constant magnitude. So it always has a constant magnitude. And yeah, that's all you basically need to say. It's come up in every exam. It's so easy to kind of get full marks for. Yeah. Of course, there's going to basically be, of course, a magnetic force that's going to be produced. So if you use because it's an electron, use your left hand. So basically, your velocity is going this way, basically. And, you know, your fingers are going to be into the page. You basically get a downwards force, basically. So at this position, there's a downwards force. At this position, there's going to be a downwards, like a, you know, force. It's always towards the center. You can see that it's like an arc of a circle. And that force is basically constant of magnitude, but it's, you know, the velocity is basically changing that direction. So it looks like a beautiful circle, arc circle. All right, so let's just write this. So what you just need to write is basically the magnetic force acts perpendicular to both velocity and magnetic field. So, and magnetic field. This force, basically this, for the second mark comes from this. This force is always present, and of constant magnitude, As a result, particle motion curves into a circular arc, Done. C. Write an equation that represents the relationship between the electron mass, the electron charge, the electron speed, and the magnetic field and the radius. Easy. We know from our formula sheet that radius is your radius of an radius is mv^3. But in this case, we got the mass, the charge has to be in E. So rub that out. It's gonna be E. The speed, yep. We've got the speed and the magnetic field. Yeah, and the radius. Done. That's an easy mark. Wow. The equations in part A and part C can be recombined to show that. Do not any attempt to derive this equation. The physics students planning the experiment keep the uniform magnetic field constant. They vary the voltage V0 and measure the resulting radius of the circular part of the electrons. Identify independent variable, the dependent, and the control. What a beautiful question. So remember, your independent variable is the variable that we are manipulating, and so they just told us they vary the voltage. So your voltage is basically your independent variable. Your dependent variable is what we're trying to measure. And so it says, and measuring the resulting radius. So, radius, which is R. Control variable is the variable that we basically keep constant, and they've already told us that. It's our magnetic field. This is a nice question. They've kind of written it beautifully. The table below shows the values of the voltage and the R measured by students. Complete the missing values. All right, all we need to basically do is square these radiuses. So let's do this one first. So 0.052 squared basically gives me 0.00 to two consecutive figures, so 27. The next one, 0.059 squared. 0.059 squared is basically 0.0035. Next one is 0.072 squared. Now it's going to give me 0.0052. Done. Beautiful. F. On the grid below, plot the values of V0 on the y-axis and corresponding values of R squared on the x-axis. Include a point for V0 equals 0. So we need to include that. Where is that? So if V0 equals 0, let's look at back in the formula. Your radius has to be 0 because all these are constants. So if your velocity, your V0 is 0, your R should be 0. So let's put the point R. There we go. Just right there. Label the axis correctly. Add any uncertainty. So add an uncertainty bar for plus or negative of this to the R squared values. Draw a straight line of best fit through the plotted points. Beautiful. So what I'm first going to do is basically label everything. So I know that the y-axis is V0, which is basically your voltage. So V. Measuring your voltage. That looks good. Actually, let's see how much do it. Let's first label the... Think about how the axes are properly calibrated. So we know the volts are going by 500, 1000, 1500 to 2000. So I can basically say if that's 500, 1000, 1.5, 2000. Yeah, that's enough. It does, and basically each go by 100. That looks good. So let's do that for this one. So basically each will go by 500 volts. That'll be then 1000 volts, 1000, 5000, 2000 volts. And then this one here is going to be 5000, and this one's 3000. And so volts are just, yeah, in that unit. Next one is your radius squared, which is basically 0.0. It's such a small number. So I want to write it in like, okay, I can write this as 1.3 times 10 to the power of, so 1, 2, 3, -3. So we can write it as that, basically. And we can do it for all of them, basically. So that's going to be just basically 2.7 times 10 to the -3. That's 3.5 times 10 to the -3. And that's going to be 5.2 times 10 to the -3. And so it's much better to kind of label them as 1.3 than that 0.0. It just makes it more harder, so I'm going to do that. So basically your radius, and they're going by what? So the max is 5.2. So what I'm going to do is basically, okay, let's think. If I consider each one, so 1, 2, 3, 4, 5. Yeah, that's enough. So 5 each. So that becomes basically, 1, 2, 3, 4, 5, 6. The unit here is basically, of course, r squared. And so the unit is, make sure you write times 10 to the -3. So all our things are times 10 to the -3. And basically it's m squared, it's the unit. Is that right? Yep, m squared. Beautiful. So, yep, those units 1, 2, and 3 times 10 to the -3. They look good. And then now, let's label those points. So, okay, the first point is 500 volts. So 500 volts is what? This over here. Well, that's not, why is it not drawing it? So I'm just going to draw a straight line. So 500 volts, it gives me 1.3 basically. 1.3. So basically each square is base 0.2. So 1.3 is what? So 1.3. That's 1.2 here. So this is here is 1.2. So 1.3 is in the between here, the middle here. So let's draw a point on it. That's it. Next one. 1000. Basically 1000 volts. Why is it rubbing off? So 1000 volts. That's going to give me 2.7 basically. 2.7, so that's 2, 4, 6. 2.7 is around in the middle here. That's it. Next one. So 1500, so it's here, is going to be 3.5. So 2, 4, 3.5 is right. Oops, what's that? 2, 4, 3.5 is right there. Beautiful. Let's rub that off. And the last point is 2000. That's 2000. And it's 5.2. So 5.2 is 5. 5.2 is right here. Oops, right there. There it is, right there. And that's it. That's nice. And so now we're just going to draw this uncertainty bars. There's only uncertainty in the r squared values. So it's 0. Basically that's 1, 2, 3. Basically 0.2 times 10 to the -3. Yes, that's basically each one square. So, let me write that out. It's basically, if I just draw one here, so basically if that's here, it's basically the values between these. So that's your uncertainty. So I'm going to basically take this here. I'm going to duplicate them and shove them all in here. So that's for the first one here. Next one, duplicate that. Oops. For the first one here, second one here. Duplicate that. Duplicate that. And that is it. I mean, that's nice. And I'm going to just delete this. And so, I'm going to draw a straight line that passes through all these points. All right, so it has to pass through 0. 100% guaranteed to pass through 0. So, let's see. If I start from 0, maybe, and start to see. If I put it right in the middle. It doesn't pass through the other one then. So, we need to move it. Yep, right there. Basically, just perfectly there. It just touches those ends. So, it does pass through it. And yeah, I think that's the best part here, yeah. That's the best line of fit. You can draw the straight line because it passes through nearly all those points. So basically, it does pass through all those points. Yeah. Let's just check. Label the axis correctly. We've plotted those values, uncertainty bars, and draw the straight line. Beautiful. Use the graph produced in part F. Calculate the gradient of the line of best fit. Show you working out. Easy. So we know that gradient is basically we need to pick 2 points on the straight line. Let's pick a nice 2 points. All right, so the 2 points that look nice is, straight away, I see this one here. Oop, why did I rub that out? So this one over here. That. Another point that I see is basically this point. That. And that. So, what's the value? So that is 1,600. So 1,600 minus 800 volts. And so your change of x is basically 4 minus 2. So basically just 2 times 2, 10 to the negative 3. Make sure you don't forget that times 10 to the negative 3 part here. And so now that gives me the gradient, which is 1,600 minus 800 over 2 times to the negative 3. So it gives me 4.0 times 10 to the power of 1, 2, 3, 4, 5. The power of 5 volts per meter. Beautiful. Use the value of the gradient found in part G to find the value of E over M. Show you working out. Okay, so what does our gradient actually represent? It just represents the V, the change of this over that. So your V's, your voltage, your V naught divided by your V naught divided by your R squared, basically. Yep, your x-axis, so R squared. This is our gradient. So using the formula that we had, we have to just kind of rearrange it. So V naught is equal to, let's write that, that's all. So V naught is basically equal to EB squared. Let's see, EB squared, then multiplied by R squared, I saw. So basically EB squared, R squared over 2M. Done. Over 2M. All right, so we want to basically get this here. How can we do that? Well, if I divide both sides by actually R squared, have a look at this. This basically cancels out. Guess what we get? We get the same as this. So what we can do is our gradient, which is our 4.0 times 10 to the power of 5, should be equal to this here, which is EB squared over 2M. All right? Okay. So, we want E over M. So, we've nearly got it, but we just need to get that B squared and 2. So, what I can do is, if I multiply actually both of those sides, so if I a little bit move this, if I multiply both of these sides by 2 over B squared, what happens is these 2's cancel out, and these B squareds cancel out, so we're left with E over M. So basically 2 over, so 2 times 4.0 times 10 to the negative, times 10 to the power 5, sorry, and your B squared. What's your magnitude of your, 2 millitesla, so 2 times 10 to the negative 3. 2 times 10 to the negative 3 being all squared. So that is going to be equal to E over M. Done. So 2 times that over 2 times 10 to the negative 3 squared. So that gives you basically 2.0 times 10 to the power of 11. Beautiful. And that is it for this exam. I actually found it very nice. It wasn't too bad. I hope you guys enjoyed this video. Please make sure to like and subscribe for more future videos, and I hope this video finds you well, and make sure you take care of yourselves. Bye bye.